Let's do a computation of a Jacobian. We need to learn how to utilize some of the aspects of the change of variables theorem. And so what we're going to do is we're going to start with a one-to-one transformation, t, and usually the notation has to be set up ahead of time, and this is what we're going to do as we work through these types of problems. S is going to be a region in the UV plane, and R is going to be a region in the XY plane. So we'll just go ahead and set that up for the remainder of the lectures on this topic. And our notation will look like this. The Jacobian will actually be written with partial derivative signs. So for instance, if we have a transformation from S to R, we'll just call the two coordinate functions x and y, which will actually be functions of u and v. And so what we think of is the Jacobian determinant, where we're actually applying partial derivatives to the functions x and y, which are written in terms of u and v. And so the definition, here's the fancy notation for it, and the definition is just the determinant of this Jacobian matrix. And notice that this is just a matrix of partial derivatives, where the first column is the column of u partials, and the second column is the column of v partials. And so when you do the 2 by 2 determinant, by definition, this is just the crisscross, which is x sub u times y sub v minus x sub v times y sub u. And of course, these are just the shorthand notations for partials with respect to u and v. Now, for the inverse transformation, that is, we're going to assume that this is one-to-one, we'll just be going in the opposite direction. And the theory tells us, and it's not very difficult to prove this, that if we look for the Jacobian of this transformation, it just turns out to be the reciprocal of this one. So here I've just written -1 as the reciprocal. So when we're working change of variable problems, we will find that this will be very useful and cut down on the amount of work that we have to do. So let's look at a particular transformation. So we have a transformation t from S into R defined by the following. That is, x is u times v reciprocal, and y is just u plus v. Now, if we follow the definition, we do the column of u partials and the column of v partials. So when we take the u partial here, we just get v to the -1, and the u partial here is just 1. Now we take the v partial of this, so we use the power rule, so that'll be a negative uv to the -2, which we have here, and then of course the v partial here will just be 1. And then we do the determinant, crisscross so to speak, so this will give us v to the -1 minus, so we'll get plus uv to the -2. And if you like, you can go ahead and retire the negative exponents by taking reciprocals here and then getting a common denominator of v squared. So we'll have u plus v divided by v squared as the Jacobian. Now, what we want to do is make a couple of observations here. If x is equal to u times v inverse, we can just cross multiply and have u equal to xv. And then of course we know that y equals u plus v. So if that's true, we can just substitute xv for u here and then factor and get that y is equal to v times x plus 1. And then of course we can divide by x plus 1 and have a formula for v. That is, v is equal to y divided by x plus 1. And now of course u equals xv, so all we have to do is to multiply v by x to get u, and that will give us u is equal to xy divided by x plus 1. So what I wanted to show you is that when you have the one-to-one transformation algebraically, in most cases, you will be able to actually solve for the formulas for the inverse. And I just wanted to show you the technique is just based upon algebra. So that's just a side calculation. Now, as we've written up here, if we wanted the Jacobian of this particular transformation here, that is the inverse transformation which I've written here, we take the reciprocal of this one. And so when we reciprocate this, we just get v squared over u plus v. And that's fine, but it's not in the variables that we like. So basically, since we've actually solved for the inverse transformation, we can substitute. Now v squared will just be y squared divided by x plus 1 quantity squared, which we have here. And then u plus v, well, we know u plus v is just y, so we reciprocate that 1 over y, and the y absorbs into the y squared, and that gives us y divided by x plus 1 quantity squared. So we have the Jacobian for the inverse transformation. And we are done.